Okay, we'll go ahead and get started. Can everyone hear me and see the screen?
Yes.
Thank you. So what I'd like to do today is I'd like to review exam 4, and then we'll finish up chapter 9, and then we should have time to start on chapter 10. So that's the plan for today. Then on Monday, we'll finish chapter 10, and then next Wednesday, we'll have our last exam, which is exam 5, and that will cover chapters 9 and 10. And then that following Monday, December 7th, we'll have the final exam. The final exam for this class is between 8 and 10 a.m. The other thing I wanted to mention is that we have one more quiz to take, quiz 5, and that'll cover chapter 9. That will be a take-home quiz. And so that'll be available on Canvas this afternoon at 1. And then you'll have until Sunday night at 11:59 to turn it in. So the quiz is take home, open book, all that stuff. There is no time limit on when you take the quiz, but you do only get one attempt at the quiz. So that means once you start on it, you need to sit there and work on it until you're finished, rather than work on part of it and then come back to it later. So any questions about any of that information? Okay. So let's go through exam 4, the answers to that. The first question was describe the difference between a polar covalent bond and a non-polar covalent bond. What it was looking for here is some kind of answer where you said that in a non-polar covalent bond, the electrons are shared equally, and in a polar covalent bond, one of the atoms attracts electrons to itself, a little more so than the other atom. So it's that uneven distribution of the electrons is the difference. Number 2, electronegativity is the ability of an atom in a molecule to attract electrons to itself, and that is true. Number 3, the greater the difference in electronegativity, the greater the bond length. That was false. Number 4, what is a simple approach to determine if a compound is ionic or covalent? The easiest way is, in general, if it's a metal plus a non-metal, it's ionic. If it's a non-metal plus a non-metal, it's covalent. Number 5, in ionic bond formation, the lattice energy of ions increases as the magnitude of the ion charges increase and the radii decrease. So it was increase, increase, decrease. Number 6, which of these bonds is the most polar? The answer is HF. We remember that in electronegativity, that upper right-hand corner is the most electronegative atom. Number 7, the Lewis structure of N2H2 shows, and the answer is each nitrogen has one non-bonding electron pair. So if you drew out the Lewis structure for this, you'd have 2 nitrogens double bonded to each other with a hydrogen off of each nitrogen, and then one lone pair of electrons off of each nitrogen. Number 8, how many electrons are in the Lewis structure of the nitride ion, NO2 minus? So the nitrogen contributes 5. Each of those oxygens contributes 6. So that's 12 from the oxygens. And then you needed to remember that because it's negatively charged, there's one additional electron that it's picked up. So if you add all that up, you get a value of 18. Number 9, resonance structures differ by, the answer is placement of electrons only. So the example that we talked about in class and also looked at in the lab was benzene. So if you think of benzene, you think of those electrons kind of being shared in the ring. Number 10, the oxidation number for iron and Fe2O3 is, the answer is +3. And we get that because we know that oxygen, unless it's peroxide, is always going to be -2. So -2 times 3 gives us, for the 3 oxygens, give us -6 charge. So that means the Fe2 has to be a +6 charge contribution. And so since there's 2 of them, that would mean Fe by itself is +3. Number 11, which of the following Lewis structures would be an incomplete octet? And the answer is B, Cl3. So in that case, you have the 3 chlorine atoms around the boron. There are no lone pairs or anything like that. So it's just 3 pairs of bonding electrons for a total of 6 electrons around the boron. Number 12, bond enthalpy is always positive. It takes energy going in to break a bond. That's why it's always positive. Number 13, what's the electron configuration for cobalt +2? So cobalt itself would be the argon core, 4s2, 3d7. The 2 electrons that we lose, because the +2 means we've lost 2 electrons, they come out of that 4s orbital, leaving us with argon core and 3d7. Number 14, the Lewis structure of PF3 shows that the phosphorus atom has 1 non-bonding and 3 bonding electron pairs. So that Lewis structure would be phosphorus singly bonded to each of the 3 fluorine atoms and then a lone pair of electrons left on the phosphorus to complete that octet. (15) Screening of the nuclear charge by core electrons and atoms is more efficient than that by valence electrons. And if you think about it, that kind of goes back to some of those Slater rules where the core electrons were the higher value, the 1 in that, than the valence electrons were. Number 16, bonding atomic radius generally increases as we move down a group and from right to left across the period. And so this has to do with the effective nuclear charge, and it has to do with the distance of the outer electrons from the nucleus. In other words, that bigger quantum number. Number 17, calculate the effective nuclear charge for sulfur. The answer was 6. So the atomic number of sulfur is 16. There's 10 core electrons, so you just subtract that. So you were not asked to do this using any Slater's rules or anything like that. So if you did do it using Slater's rules and you did it correctly, then you got some partial credit. If you used Slater's rules and did it incorrectly, then you didn't get any credit. Number 18, the bonding atomic radius or the covalent radius is half the distance between nuclei in a bond. That's true. 19, the electron affinity is the minimum energy required to remove an electron from the ground state of a gaseous atom or ion. That's false. That definition is the ionization energy definition. Number 20, metals tend to form cations because we know they like to lose electrons, and nonmetals tend to form anions because we know they like to pick up electrons. Number 21, most nonmetal oxides are acidic. That's true. Number 22, when alkali metals react with water, the reaction is known to be, the answer is exothermic. So remember, the alkali metals are sodium and potassium and things like that. And we had talked about how those are pretty violent reactions when those metals are placed in water. 23, lithium plus ion is smaller than lithium. That's true, because by plus we then know those cations we know have lost some of the valence electrons. 24, which was probably everyone's favorite question on the exam. Write the balanced chemical equation for the reaction of dichloroheptoxide and hydroxide. So first thing you needed to do was figure out that dichloroheptoxide was Cl2O7. And the other thing you needed to remember was, if we go back up to 21 here, we said most nonmetal oxides are acidic. So this is a nonmetal oxide, so we know it's acidic. So it'll react with OH. You also may have remembered that nonmetal oxides react with base to form salt and water. So those were some clues there. It was a little bit of a tricky question, and so there was partial credit there. It's also an example of where, you know, it is an open book test, so you have some other resources available. But I will say, you know, someone asked if there should be some other cation associated with the hydroxide. That was purposely left off, the cation. And so if you used another resource to get what the reaction was, but had, say, a sodium in front of the hydroxide or a sodium in front of the perchlorate, you lost points because that wasn't part of the question. So the answer is you form two perchlorate ions plus water. Number 25 through 29. Oh, the other thing I'll say about 24 was related to one of the homework questions that you had, just as 25 through 28 was one of the homework questions. And so a couple of things I'll say about that is in the homework in the book, there was the Lewis structure was drawn with bromine single bonded to each oxygen, and then one lone pair of electrons on the bromine. So the answers you see here are for if you approach the problem that way based on how the homework was done. Actually, the more correct way of drawing that Lewis structure for bromate is bromine double bonded to two of the oxygens and single bonded to one of the oxygens. And this goes back to calculating out the formal charges on the bromine and the oxygen And remember, we always say we want the formal charge to be as close to 0 as possible. So with the 2 double bonds and the single bond, you actually get a little bit better formal charge value that way. So if you did do it that way and you did it correctly, you got credit as well. But going through it, the answers for the 2 approaches, in each case, there were 26 valence electrons. So you needed to remember that it is a negatively charged ion, so that you had the valence electrons from bromine and the 3 oxygens, but also you had 1 additional electron because it's an anion. 26, what's the formal charge for bromine? So remember, we calculate formal charge by taking the number of valence electrons minus 1/2 the bonding electrons minus the number of lone pair electrons. And so if you did the approach of 3 single bonds, then you would have a value of +2. If you took the approach of 2 double bonds and a single bond around the bromine, then that would work out to be 0. So it'd be 7 minus 1/2 times 10 minus 2. For 27, what's the formal charge for oxygen and BrO3? Once again, if you did the single bond approach, the answer is -1. So you have 6 valence electrons minus 1/2 times 2 bonding electrons minus 6 non-bonding electrons. If you did do the 2 double bond, 1 single bond approach, then you should have a second value for this, because you would have the -1 for the single bonded oxygen, but then the double bonded oxygens, you would have a value of 0 for those 2, because in that case you'd have 6 minus 1/2 times 4 bonding electrons minus 4 lone pair electrons for a value of 0. So 26 and 27, you could get those answers 2 different ways depending upon which Lewis structure you use. So I gave credit for each of those. 28, what's the oxidation number? What's the oxidation number for bromine? And then 29, what's the oxidation number for oxygen? In each of these in BrO3 minus. As we talked about in class, oxygen is almost always -2 for the oxidation number, unless it's a peroxide. And so for me, I answer 29 first and know that oxygen's -2. If my oxygen is -2, then I have 2 times 3 is, there's 3 oxygens, so that's a -6 contribution from the oxygens. The overall ion has 1 negative charge, -1 charge, and so that means bromine would have to be +5 to get that minus charge. So any questions about any of the things on the exam? Okay. Let me pull up the chapter 9 slides then, and we'll finish that off. Okay. We started talking about molecular orbital theory on the last lecture, and I felt like I was getting a little rushed on that. So I wanted to go back and kind of start from the beginning on the molecular orbital theory. And so, up until now, we've been talking about orbitals and all that. We've been talking about it in terms of the atoms themselves. And so molecular orbital theory, while it's a similar type of of approach. Now we're talking about the molecule as a whole rather than just the atom individually. So I wanted to make sure everyone kind of understands that distinction. And so we'll kind of go back to the beginning of the molecular orbital stuff and finish that off today. So the molecular orbitals have a lot of the similar characteristics as atomic orbitals. We have things like a maximum of 2 electrons per orbital. We have the thing where the electrons in the same orbital have the opposite spins. In other words, one arrow up, one arrow down. We have definite energy levels of the orbitals, and we can do some of these electron density plot type diagrams. So very similar to the types of things we talk about in atomic orbitals, just in this case now it's the molecule as a whole. So as I said, the differences are that instead of talking about those individual atoms, we're now talking about the whole molecule. And whenever 2 atomic orbitals overlap, we have 2 molecular orbitals are formed, and we call one a bonding orbital and one an anti-bonding. And the bonding orbitals, those are what we call constructive or additive combinations of atomic orbitals, and these will be lower energy, and because they're lower energy, they're more stable. And it's those bonding orbitals that we use to tell us if a combination of atoms really is going to form a stable bond or not. The anti-bonding orbitals, we say that those are destructive combinations, and you think of destructive, that's a negative term. And so now what we start to see because of that is that we see these nodal planes. And the nodal plane is just something that tells us that there's no electron density in those occurrences. So remember, when we have these electron density plots, we're using math to predict where the electrons may or may not be. So in that nodal plane, the math is telling us that there is no electron density there, so there's no chance of the electrons being there. The way this works out, that these are higher energy orbitals, and because they're higher energy, they're less stable. And so if we say something is less stable, we're saying that it's less likely to exist. So that's the difference between the bonding and the anti-bonding. It's really that stability and that energy level. So let's take a look at how this looks in a simple combination of 2 hydrogen atoms. So we talk about that we have direct overlap of the orbitals, and when we do that, we get a bonding and an anti-bonding orbital. This combination is called a sigma molecular orbital. And so in this diagram, we see on the left representations of the 2 1s orbitals from the 2 hydrogen atoms. Then we go ahead and combine those. So we have this overlap of those orbitals, and we see on the right the constructive and destructive combinations that we just talked about. And so we have these electron density plots that we see. And so the lower one, that's our constructive combination. And so our bonding combination, and we see electron density in between the 2 nuclei of the 2 hydrogen atoms. Up above, we have that anti-bonding orbital. So that's that destructive combination. And we see the dotted line in the middle, and we also see this gap of electron density between the 2 atoms. And it's that gap in the middle, that's what we were calling our nodal plane. And since we don't see any blue there, that tells us that there's no mathematical possibility of electrons being there. So if there's no electrons being shared there, then obviously there's not a bond taking place, and thus the name of an antibonding orbital. When we designate this, we use that little sigma sign for the bonding orbital, and then sigma with a little asterisk above it for the antibonding. So when we do this kind of molecular orbital diagram, we do it based on energy. And remember, we said the bonding are lower energy, the anti-bonding are higher energy. So the way this is typically drawn is, as you see in the figure on the bottom, on the left-hand side, we have representation for one of the hydrogen atoms, representation on the right-hand side for the other. We see the one on the left, we have one electron there, because we know a hydrogen atom has one electron. And then on the right-hand side, we have the spin going the opposite direction for that hydrogen atom. Because remember, we said the spins pair, just as we did in the atomic orbitals. And so we combine those two into our molecular orbital. That's the kind of reddish, pinkish boxes in the middle. So the two yellowish boxes on the side represent the atomic orbitals. The ones in the middle represent the possibilities for these two, that we can have two possibilities. We can have the bonding molecular orbital, which is the lower energy one, the sigma 1s at the bottom. And we can have the anti-bonding molecular orbital, which is the sigma star 1s up at the top. So we go ahead and pair those electrons, and both of those electrons will fill up that bonding molecular orbital down at the bottom. So we have the two electrons in the bonding molecular orbital, and we have no electrons in that anti-bonding. So what this suggests to us, since we have filled the bonding molecular orbital, this suggests to us that this must be a stable molecule, H2, and we know that it is, but this is the molecular orbital theory which demonstrates this. There is a calculation that we do with these molecular orbital diagrams, and that's something called bond order. And bond order is just 1/2 times the number of bonding electrons minus the number of anti-bonding electrons. So in this case, for the two hydrogen atoms, we have two bonding electrons. That's in that sigma 1s down at the bottom. We have no anti-bonding electrons. That's the anti-bonding molecular orbital above. So that would be 2 minus 0 would be 2. And then half of that equals 1. So that tells us that the bond order is 1 bond. If we get a value for bond order, then that tells us that it's stable. If we get a bond order of 0, then it's not going to be stable, and we're not going to have that molecule form because of the energy diagram that we have. So here's another example of looking at a simple diatomic molecule to see if we think it really exists. So we just looked at hydrogen and saw that H2 exists. Now let's go up one more on the periodic table, and let's look at helium. So remember, helium, that helium atom has two 1s electrons. So we go ahead and draw our molecular orbital diagram. So we have on the left and right representations for those helium atoms. In each case, we have a pair of electrons in the 1s orbital. Then in the middle, we have the bonding and anti-bonding molecular orbitals that we draw. And those, the bonding is lower energy, the antibonding is higher energy. and we go ahead and fill those with the 4 electrons. So we put 2 electrons in the bonding molecular orbital at the bottom. We put 2 electrons in the antibonding. So we've accounted for our 4 electrons from the 2 helium atoms. And so then if we go ahead and calculate our bond order there, we have 2 bonding electrons minus 2 antibonding electrons. That's 0. So that 0 times a half is 0. So that tells us there's 0 bonds possible for this combination, this helium-helium combination. What that does is that tells us, based on this molecular orbital energy diagram, that He2 does not exist. So, and we know that helium exists just as He, not as He2, whereas hydrogen exists as H2, not as just H. So for these 2 gases, the molecular orbital diagram tells us, by doing that bond order calculation, whether the diatomic versions are possible or not. So some things that we want to remember when we're talking about looking at to see if molecular orbitals are possible and how to form them. First thing is the number of molecular orbitals formed equals the number of atomic orbitals combined. Atomic orbitals combine with atomic orbitals of similar energy. So in the 2 cases we looked at, it was pretty straightforward because we were looking at diatomic molecules. So we were looking at molecules that had the same atom, either hydrogen or helium in the second case. So those energy levels are going to be the same. If we had different atoms that we were looking at, then we would have to make sure that the energy levels that we're combining are atomic orbitals that are similar in energy. Number 3, the effectiveness with which the 2 atomic orbitals combine is proportional to their overlap. As the overlap increases, the energy of the bonding molecular orbital decreases. And 4, each molecular orbital can accommodate at most 2 electrons with opposite spin. So this is that Pauli exclusion principle, where we say one goes up, one goes down when those electrons pair. So that's similar to what we did in the atomic orbitals. And then at 5, when molecular orbitals of the same energy are populated, you get 1 electron entering each orbital. In other words, each one gets filled with the spin pointing up before they start pairing. And once again, that's Hund's rules that we learned for the atomic orbitals and filling those orbitals. So it's the same idea here. So this goes back to what we said in the beginning, is that some of these rules and some of the things that we saw in the atomic orbitals kind of carry over through to the molecular orbitals. The big difference is, instead of just talking about an individual atom, now we're talking about the molecule as a whole. So let's talk a little bit more about this molecular orbitals and bonding and how the core electrons factor in. And remember, when we talk about the core electrons, we're talking about, if we go back to the periodic table and look at the electrons that lead up to fill one of the noble gas electron configurations, those are the electrons that we've been calling the core electrons. So we had the core electrons and we had the valence electrons. Now what you're going to see here, and you'll see it as we go through this lithium-2 example, but what you see is that the core electrons versus the valence electrons, once again, the valence electrons are where kind of all the activity is occurring. And so the core electrons, we really don't see playing much of a part in the bonding. It's those valence electrons. So lithium-2 is possible. It's not common, but it is possible. And if we look at the molecular orbital diagram, we see that on the left, we have the atomic orbitals for one of the lithium ions, or the lithium atoms. On the right, we have the atomic orbitals for the other lithium atom. And so in each case, we have 2 electrons in the 1s orbital and 1 electron in the 2s orbital. And so if we go then and then draw our molecular orbital diagram in the middle, we would have sigma 1s bonding, sigma 1s antibonding. Then we have the 2s bonding and antibonding orbitals. And we would draw those out like this. We know the 2s is higher energy level because that quantum number is bigger. So it's a 2 quantum number versus a 1. And so if we go ahead then and fill in those 3 electrons from each of the 2 lithium atoms, we'd first fill the sigma 1s, then the sigma star 1s. So that's 4 electrons. Then we have 2 more electrons. So those would go in the sigma 2s. And what we see here is that if we went ahead and did our bond order, we'd get a value of 1. But what we see is that this tells us that it is stable. Well, the other thing that you'll notice is really those 1s electrons basically just cancel each other out. And so we're not that concerned about those. And a lot of times when we draw these molecular orbital diagrams, we'll just focus on the valence electrons. Because really in this example, it's those 2s electrons that are determining whether this is possible or not. So up until now, we've been looking at just the s orbitals. The p orbitals can also undergo overlap, and we get a little bit different, a little more complicated density plots when we start looking at those. So let's take a look at that. Because there's a couple different ways that these p orbitals can overlap. And the way they overlap goes back to that orientation of these p orbitals. When we think back to how the p orbitals were oriented in the atoms, remember there was a 3-dimensional component to it where we had ones that were along the z-axis, along the x-axis, along the y-axis. And so that's what we want to take a look at here. And that spatial orientation is why we have the different the spatial orientation is why we have the different types of overlap. So if we just had 2 atoms that we are going to say we have p atomic orbitals, we would have a bonding molecular orbital and an anti-bonding molecular orbital. And remember, we said that the bonding ones are additive, the anti-bonding are not. So if we look at the pz orbitals first, the 2 pz in this case, we see that those lobes on the pz orbitals would overlap to form kind of that bigger balloon shape. In other words, greater electron density in between the 2 nuclei. For the anti-bonding one, remember we said on the anti-bonding, it's more of a destructive type of overlap. And so in that case, we wind up with small amount of electron density, and in the exact middle of it, there's no electron density. So that's telling us there's no bonding taking place there. So that PZ one kind of looks similar to what we might be used to seeing. And that represents more of a sigma type bond that we would see. If we look at the next 2, the PX and the PY orbitals, then we start seeing what we talked about when we talked about double bonds and triple bonds and things like that. We're starting to get into the pi bonds. So it's not the sigma bond anymore, it's now the pi bonds. And remember how we talked about what that looked like. And here we get a really good representation of it, I think. So let's look at the X orientation first. So we see that's the 2 vertical p orbitals. When it's a bonding overlap, then we see that above and below the plane of the nuclei, we have electron density overlap. So that winds up with that kind of electron density lobe above and electron density lobe below the plane of the nuclei. We see above in the antibonding that because that is antibonding, we don't get that overlap to form the pi bonds above and below. We actually have that nodal plane in there, which tells us there's no electron density. If we look at the one on the bottom, the Y orientation, we see a similar thing, except just because of how these are oriented, now we have overlap where, and it's a little hard to see in this picture, but what you have is you have a lobe kind of in front of the plane between the two nuclei and a lobe behind it. So we've got, once again, that's that pi bond type lobe that we talked about when we were talking about single, double, triple bonds. And then above, we see that there is a nodal plane there as well, where there's no electron density. And so then no bonding taking place. So the p orbitals, at least for me, are a little harder to visualize. So these pictures help a little bit, but still it's a little tricky. The takeaway is that first one, the Z, is giving us a sigma bond, and the others are more the pi bonding that we talked about. So what does this look like in terms of a molecular orbital energy diagram? So for this, we would go ahead, if we had something we were trying to figure out, and we would draw our molecular orbital diagram. We would not worry about any core electrons. In this case, we're going to say it's something in that second period. So in other words, second row of p elements. So second row of p elements would be things like boron, carbon, nitrogen, things like that. So we would have, we're not going to draw the 1s electrons because we talked before about those core electrons really don't factor into things. So we would start by drawing our 2s electrons. So we'd have 2s on the left from the atom, 2s on the right. For our molecular diagram, we would have the bonding and anti-bonding orbitals associated with those 2s orbitals. Then we would have the 2p orbitals. So in terms of the atomic orbitals, those are degenerate. So those, we're drawing those as the same energy level. So we have 3 of those on each side for each of the atoms. But then when we have the molecular orbitals, the way that energy fills is sigma 2p, then the 2 pi orbitals. Those pi orbitals are degenerate, so we draw them at the same energy level. And so that's why we have the 2 boxes there next. Then we have the anti-bonding pi orbitals, and then finally the anti-bonding sigma orbitals. So we have 3 orbitals associated with the p orbitals, similar to what we do in the atomic, but they are different energy levels. The sigma energy level is lower than the pi, the 2 pi ones. And the reason for this is that the sigma molecular orbital is because it's a better overlap. It's a direct overlap. So that impacts the energy more, it's more stable, and thus a lower energy. So we looked at s orbitals overlapping, we looked at p orbitals overlapping. You also can have an s or if you had one compound or one atom rather that has s orbital, another atom that has p orbital, you can have s and p orbital interactions. So let's take a look at that for a little bit. So at the bottom here, we show from an electron density perspective what that looks like. So we have that PZ orbital, which is usually the one that we're talking about when we're talking about this S and P orbital overlap. So we have the S orbital on the left, which is that blue circle. We have the P orbital on the right, which is that kind of looks like two pink balloons there. And we see then the overlap portion of it. From an energy type of situation, we would have sigma 2s, sigma 2s star, and then the pi bonds and the sigma 2p. So as we get more interaction between 2s and 2p, we see the energy levels kind of changing. So we see actually a flip of that sigma 2p and the pi 2p. The sigma 2s, sigma antibonding 2s kind of stay where they're at. But then when we get to the sigma 2p and pi 2p, there is a flip there. So let's take a look at what this means when we look at some of the diatomic molecules in that second period. So remember, second period, we're talking boron, boron, carbon, nitrogen on down the line. So if we look at the first three, we see B2, C2, N2. And we see there that the pi 2p is a lower energy than the sigma 2p. And that's because we have a larger interaction between 2s and 2p. As we move along and we have smaller interaction between 2s and 2p, then we see that those energy levels change, and now suddenly we have sigma 2p filling before pi 2p. And then when we get to those, we start having some of the antibonding pi orbitals as well. And then finally with neon, we actually get to the antibonding 2p. When we look at the molecular orbital diagrams, we look to see if there are any unpaired electrons or not. And whether there are or not, that introduces some terms called diamagnetism and paramagnetism. So diamagnetism is what we call when all the electrons in every orbital are spin paired. So in other words, no unpaired electrons. So if we go back to here, the F2 would be one of those, neon 2 would be one, N2 would be one, C2 would be one. We don't have any unpaired electrons in any of those molecular orbitals. The O2, the B2, those we see some unpaired electrons. So for those, we would call those paramagnetic. So paramagnetism is what we call it when there's one or more unpaired electrons in an orbital. So these molecules that have unpaired electrons, they're attracted to a magnet. And so the more unpaired electrons you have, the stronger the attractive force. So this magnetism with the paired and unpaired electrons, this is used in a technique called nuclear magnetic resonance, NMR, and we're not going to get into it in this class, but this is a way that you're able to take advantage of this pairing or unpairing, this response to a magnetic field to get information about molecules. So up until now, we've been talking about diatomic molecules, but the diatomic molecules we've been talking about have all been the same atom. Let's talk a little bit about an example of a diatomic molecule where it's two different atoms. And when we start doing that, then these molecular orbital diagrams get a little bit more complicated. Because before, when we had two atoms and they were the same atom, we knew those atomic energy levels were going to be the same. Now, with different atoms, now the atomic energy levels are going to be a little different because they're different atoms. And then that can have an impact on the molecular energy level as well. So the atom that is more electronegative, it has orbitals lower in energy. So the bonding orbitals will be more similar to their energy level. So if we look at this example, the NO example, we look at nitrogen and we look at oxygen. And if we remember our electronegativity table, we know that oxygen, because it's more in that upper right-hand corner, a little more so than nitrogen, we know that oxygen is more electronegative. So its energy level is going to be a little bit lower than the nitrogen. And we see that represented here. On the right-hand side, that 2s and 2p orbitals are slightly lower than the 2s and 2p orbitals on the left-hand side. Remember, left-hand side are the nitrogen atomic orbitals, right-hand side are the oxygen atomic orbitals. Then in the middle, we see the molecular orbitals that are a result of that NO molecule. And so we see that in this case, the sigma 2s orbital is a little bit closer to the 2s atomic orbital of the oxygen than it is to the 2s atomic orbital of nitrogen. Same as we go up to the 2p orbitals, sigma 2p is a little bit closer to the 2p for the oxygen atomic orbital, the pi 2p a little closer as well. And then we go up to the antibonding pi 2p and the antibonding 2p. So we see a little bit of shift when we have atoms in this diatomic molecule that aren't the same, and that's based on the electronegativity. So there is some homework associated with this. Take this and take a look at it. The other thing I want to point out about the molecular orbital stuff, and you probably picked up on this, but I'll just repeat it anyway, is we did a little bit of an example of a diatomic molecule that had two different atoms. We go back here, and all of these were diatomic molecules with the same atom. And we see already on this, as we started adding electrons, okay, so we didn't get very far. We got through nitrogen, and then we started seeing energy levels changing and things like that. And if you think of how we started with pretty simple stuff here. Let me go back a little bit more. We had lithium, and we had helium, and we started with hydrogen. So my point to this is, all we've looked at were diatomic molecules. We started out with just diatomic molecules that were the same atom. We didn't get very far down the periodic table, and things started to get a little more complicated. And then finally, the thing we ended on was looking at some pretty simple diatomic molecules with different atoms, and things got a little more complicated there. So my point is, and now we're ending the chapter. My point is that this stuff gets really, really a lot more involved as you get to bigger molecules, as you could imagine. So what I would like you to take away from this is just trying to understand the difference between atomic orbitals and molecular orbitals, understanding this bit about the magnetism, diamagnetism and paramagnetism, and then understanding some of this kind of stuff about the bonding, anti-bonding, when you get the overlap and the nodes that tell us that there's no electron density there, and getting a feel for what the p orbital overlap looks like, and then going back to here, the s orbital overlap looks like. So if you can get a feel for that kind of stuff, it'll be a good introduction to molecular orbital theory. So any questions on any of this before I move on to the next chapter? Okay, let me close this out, and then I will we'll get going on the chapter 10. Okay, so chapter 10 is very different than what we've been talking about the last couple of chapters. So now we're going to switch gears and we're going to talk about gases. So if you really like the stuff for the past couple of chapters, this will be maybe not a good thing. If you didn't care for it, then you might like this better. So when we talk about gases, no matter what gas we're talking about, the physical properties are pretty similar. You know, gas kind of behaves like a gas. It may have some different chemical properties in terms of reactivity or odor or things like that, but the physical properties of how they behave from a physical perspective, that's pretty much the same for all gases. Gases are usually non-metallic elements, composed of non-metallic elements, and usually the formulas, molecular formulas, are usually pretty simple, usually not real complicated, and the molecular weights are usually pretty low. Unlike solids and liquids, gases expand to fill their containers. So if you put a gas in a small container, it fills it up. You put it in a big container, it fills it up. It takes as much space as you're willing to give it. One of the things is that usually you can compress gases quite a bit. So in other words, you can, you know, if you have 100 milliliters of water, you need a 100 ml container. For gases, you can go ahead and compress it and kind of push it together to get it to fit into a smaller container. Now, as we'll learn, that'll mean the pressure goes up, but you still can fit it in the container. Gases, as you might imagine, have very low densities. So as we'll see in a moment, that's kind of one of the core definitions of gases, is that the molecules are spread out. And if they're spread out, we learned before that density is mass per volume. So if things are spread out, then we know that density is going to be low. If you have a mixtures of gases, two or more gases, they're going to want to form a homogeneous mixture. So remember, we talked about with some of the liquid solutions that you could have heterogeneous mixtures of where you had solids and you had the liquid and you could maybe filter it out or something like that. With gases, those gases like to mix and become homogeneous. Now, it may take a little bit of time for the mixture to become homogeneous, but the gases are trying to do that. There's a whole bunch of common gases that we talk about, and these are ones that are gases at room temperature. So some of them, hydrogen cyanide, HCN, that's very toxic. Hydrogen sulfide, that's that H2S, that's that rotten egg gas smell that you may get sometimes. Carbon monoxide, that's the one that people worry about in there. their homes, that you'll hear periodically someone will get injured or killed because they breathe it. Problem with carbon monoxide is that it is odorless and it's colorless, so you don't really know it's there until it's too late. CO2, we hear about CO2 emissions all the time. Once again, it's colorless and odorless. Methane, that's a flammable gas. Ethylene, the C2H4, that's an interesting one. Ethylene is what they will expose fruit to ripen it. You hear about that with bananas all the time. And propane, propane is what you use if you do have a gas grill. Nitrous oxide, you hear that laughing gas sometimes, dentists and that'll use that a little bit. Ammonia, sulfur dioxide. A couple things I'll say here is that one thing I want to point out is most of these gases, as you can see, are colorless. And so it's always interesting because a lot of times people will see things coming out of smokestacks and things like that and wonder what that is. A lot of times that's just water vapor that you see condensing. The gases that you really worry about, like some of these on this list, as you see, they tend to be colorless, so you would not see them if they were coming out of a stack. Okay, well, the gas that most of us deal with and think about is air. So what is air? So when we think of the air that we breathe, the atmosphere, it's actually mostly nitrogen, N2. So it's, by volume, it's approximately 78% nitrogen. Oxygen is only 21% of that. So the air that we breathe, even though we say I need oxygen, because you do need oxygen, the air we breathe is mostly nitrogen. And then oxygen is the second most prevalent component. There's a whole bunch of other things. There's a little bit of argon, a little bit of CO2, neon, helium, and an assortment of others, but you can see on a percentage basis, those others are pretty small. So it's mostly nitrogen, followed by oxygen. So when we talk about the state of a gas sample, there's 4 ways that we describe it and help define what the state of that gas is. One is temperature, the other is pressure, another is volume, and then the fourth is the amount of gas. And when we talk about gas, we usually talk about the number of moles. So in the past, we've talked about temperature, we've talked about pressure, or rather, we've talked about volume, we've talked about moles of stuff. So we're going to focus a little bit more on pressure because we haven't talked about pressure much. So when we think of gas molecules are always moving around. That's why they're gases. And so as they move around, they collide with each other, and they also run into the walls of the container. So think of it as, you know, if you had a bunch of people in a room and they were just kind of running around, they're going to run into each other a little bit. They're going to run into the walls a little bit. That's what gas molecules are doing. They're never stopped. They're always moving around. And during that running around, they might run into each other or run into the wall. The sum of all these collisions is what we call pressure. And pressure is the amount of force per unit area. Atmospheric pressure is the weight of air per unit area. So pressure is directly proportional to the number of gas molecules in the air. So once again, pressure is related to the number of those collisions, but really what we're saying is the more molecules we have, the more collisions we're going to have. So what we're really talking about with pressure is how many of those molecules are in a defined area. So in some ways, it's kind of similar to density. You can think of it that way. Not exactly the same, but it's kind of the same idea. when we talk about pressure, there's a whole bunch of units that people use. They use pascals, they use bar, they use millimeters of mercury, that's the mmHg. That millimeters of mercury is also known as torr. And then we have atmospheres, ATM. So you'll see any of these used, depending upon who's talking, you'll see different of these. There's also, so there's just a lot of ways that people express this. So whether it's pascals, bar, millimeters of mercury, torr, atmospheres, any of those, don't be confused. They're all talking about pressure for gases. The millimeters of mercury is an interesting one because there's a diagram here that shows a way to measure pressure, and you'll hear the weatherman talk about a barometer, barometric pressure, things like that. This is the kind of thing they're talking about, something similar to this. And that millimeters of mercury unit came from literally doing this measurement when you have atmospheric pressure versus the other two, and measure that difference of the height of the mercury going up. So you have, on one side, you have the pressure on this mercury that's exerted by the atmosphere. The other side is a tube that's been evacuated, and then the mercury goes up or down depending upon how much pressure is exerted on that pool. That pushes up that mercury in the tube, and then that height that you measure from the pool of mercury to the top of a mercury in the tube, that's the millimeters of mercury, and that's where that measurement comes from. When we talk about atmospheric pressure, standard atmospheric pressure, that is defined as 1 atmosphere, or 760 torr, or 760 millimeters of mercury. And so you'll see as we talk about some calculations here, we'll mostly use atmospheres for our calculations as the units that we do. There's something called a manometer, and that's used to measure the difference between atmospheric pressure and the pressure of some gas that you're trying to measure. So you have gas in some type of container, and you can use this manometer to measure the pressure inside that container. It works, it's kind of similar to the barometer that we saw on the previous slide, similar idea, except in this case, as you can see, is you have this tube, and in the tube there's some mercury in there, and then you hook one side of the tube up to the container you're trying to measure. The other side is open to the atmosphere. So think of it as on that open end, you have the atmospheric pressure kind of pushing down on the mercury. On the other end, where you've connected it to the container, the pressure that's in there is pushing out onto the mercury. And so it's kind of like this tug of war between the container and the atmosphere. And that difference in height of the two levels of mercury plus the atmospheric value, that tells us what the pressure of the gas is. Okay, let's talk a little bit more about these properties of gases. So when we talk about pressure, we usually designate that with the letter capital P. As I said before, the amount is usually measured in moles, and that's represented by a small n. Volume is usually represented in liters and represented by a capital V. And temperature, and this is an important thing, is when we talk about gases and gas calculations, we always express the temperature in Kelvin. So similar to some other calculations we did before, if you don't switch it to Kelvin, the calculations don't work out correctly. So if you leave it in percent, or rather degrees C or something like that, the formulas don't work. They have to be in Kelvin. And remember, Kelvin is degrees C plus 273. What we know is that if we change one of these things, the other properties change. So if you change the number of moles, you change the volume, you change the temperature, you change the pressure, you change any of those, they're all interrelated. And it's those interrelations that we're going to be talking about here. So the first thing that we'll talk about is something called Boyle's law. And Boyle's law tells us the volume of a fixed quantity of gas. And so by fixed quantity of gas, we mean the moles don't change. That if the volume of a fixed quantity of gas at constant temperature, that it's inversely proportional to the pressure. So in other words, if the temperature doesn't change and the number of moles doesn't change, that the volume and the pressure are inversely proportional. So what this means is if the pressure of a gas is increased, so in other words, if you increase that pressure and you haven't changed the amount of moles and you haven't changed the temperature, then the volume will decrease. And then vice versa. So the mathematical relationship for this is P1 times V1 equals P2 times V2. So molecules, and from a just what's going on perspective, this tells us that molecules in a smaller space collide more frequently with each other and the walls of their container. So that's why the pressure goes up. So smaller space, using that analogy of people in a room and running around. So remember, that's the gas molecules. If you're in a big room and you're running around, you're not going to run into each other that often. You're not going to hit the walls that often. You decrease that size of the room, you have the same number of people, they're going to run into each other more often, they're going to run into the walls more often, so that means the pressure is going to go up. So Boyle's law, P1 V1 equals P2 V2. So let's do an example of this. So if we have a weather balloon and it's inflated to a volume of 55.0 liters, and the atmospheric pressure is 755 millimeters of mercury, what would be the volume of the balloon if we change the altitude? And so by changing the altitude, we're changing the pressure. So now our pressure is 135 millimeters of mercury, and we're assuming constant temperature. So what we're going to do is we're going to say our V1 is 55.0 liters. Our P1 was 755 millimeters of mercury. Our P2 is 135 millimeters of mercury. Or rather, and so what would our V2 be? So Boyle's law tells us P1 V1 equals P2 V2. We can go ahead and rearrange that equation because we're trying to solve for V2. We plug in our numbers, we get our millimeters of mercury canceling, and we're left with units of liters. And so our final value, if we do the math, is 308 liters. So by changing that pressure, in other words, in this case, our pressure went down. So now our volume goes up. It goes from 55 liters up to 308 liters. So that's an example of that relationship that we talked about here between pressure and volume and Boyle's law. Okay, I think we're going to stop here for today, and we'll pick up with Charles' law on Monday. So once again, remember that there's a quiz. Quiz 5 is out on Canvas. It's a take-home quiz. You have till Sunday night to complete it, so please go go ahead and complete that and submit your answers. And then we'll have a nice Thanksgiving and we'll see you on Monday. If there's no questions, that's it for today. Thank you.
Thank you. Happy Thanksgiving.